Hello, myself Dr. Shaila Dinkar Apte. Let us continue with the series of the lectures in digital signal processing. So here we continue with Z transform. Now we'll go through properties of Z transform and let us see how we can predict the time domain behavior of the system based on the locations of poles and zeros of the transfer function. Let us first consider properties of Z transform. These are the properties of Z transform. First one is the linearity, then next one is the time shifting, scaling in Z domain, time reversal, differentiation in Z domain, convolution and initial value theorem. Let us go through these properties one by one. So first one is linearity property, which is same as linearity property of other transforms. That is, if we have two input sequences x1n and x2n, and if they are linearly combined as a into x1n plus b into x2n, the corresponding transforms will also be linearly combined in the same manner, and you will get the effective Z transform. Now in this case, if ROC is R1 for the first sequence and ROC is equal to R2 for the Z transform of the second sequence, then the effective ROC for the linear combination will be R1 intersection R2. Intersection means it is the common area of convergence for the two Z transforms. Now consider one example. In this case, f1n, that is first sequence, is given by e raised to minus 6n and f2n is e raised to minus 3n. We have linearly combined these two sequences. What will be the Z transform of the linear combination? So fz will be written as twice f1z minus twice f2z. What will be f1z? f1z we will write it directly in the form of closed form expression, that is 1 upon 1 minus what will be after this 1 minus, this will be e raised to minus z into z1, z inverse. For the second term it will be 1 minus e raised to minus 3 into z inverse. Now how to find the ROC? ROC will depend on this particular term. This term we equate it to be less than 1. So if mod of e raised to minus z, z inverse is less than 1, that indicates the ROC for the first term. So we can write mod z greater than e raised to minus 6 is the ROC. Similarly, for the second term, ROC will be written as e raised to minus 3 into z inverse less than 1, which implies mod z greater than e raised to minus 3. Now what will be the common area of convergence? It will be the intersection of the two areas. Let us see how we plot it. So this is the circle with radius e raised to minus 6. This is the circle with radius e raised to minus 3. Obviously e raised to minus 3 circle will be outside that of e raised to minus 6. What is the common area of convergence? It is the area which is outside the circle e raised to minus 3, because this e raised to minus 3 is outside the circle of e raised to minus 6. So this whatever is shown here, it is the common area of convergence. Now consider the property of time shifting. If we have the sequence xn and if we time shift by amount n1, so it is shifted by the number of samples equal to n1. Either we can shift it towards right or shift it towards left, depending upon whether n1 is positive or n1 is negative. Then in that case, what will be the Z transform? Z transform will be written as z raised to minus n1 xz, means depending upon whether n1 is positive or negative, there will be additional poles introduced at 0 or infinity, depending upon n1 is positive or n1 is negative. Let us consider one example to illustrate this. So consider example again, fn is equal to minus 6n e raised to minus 6n. Now what will be f of n minus 2? We just have to replace n by n minus 2. So we write it at e raised to minus 6 n minus 2. Now what is the Z transform for this fn? We write fz as 1 upon 1 minus e raised to minus z into z inverse. This is the closed form expression as we know. Now to find Z transform of f of n minus 2, we have to use the time shifting property. So how it will be? It will be Z raised to minus 2 because 2 is the amount by which we are shifting the input sequence. So Z raised to minus 2 into Fz, so 1 upon 1 minus e raised to minus z, Z inverse. So what will be effective Fz? This Z raised to minus 2, if we take it in the denominator, it will be Z raised to plus 2, and when I multiply by Z raised to plus 2, this one, see, if I take Z as the common factor out, I will have Z minus e raised to minus 6 in the denominator. So we'll have to multiply numerator as well as denominator by Z square. And we see that there is a pole at Z is equal to 0, which is additionally introduced. Hence, there is a deletion of the origin, as we can see. Now, property of scaling in Z domain. If we consider the sequence xn, which is transforming to xz with ROC is equal to R, then in that case, Z0 raised to n, this Z0 can be any constant, Z0 raised to n xn, this is what is called as scaling in, this is the multiplication in time domain, but what happens in the transform domain? It gets scaled. So it will transform to x of z divided by z0. So if I want to calculate z transform of a raised to n un, it will transform to u of z divided by a. So if ROC is mod z r, then R0 Z0 R is a scaled version of R. That is, if Z is a point in ROC of xz, then mod z is in ROC of x of z minus z. We'll come to this with examples so that you will understand. So consider example 1. Now in this case I am considering xn as un. Now what will be xz? Xz we already know that it is z upon z minus 1, or we can write it in the closed form as 1 upon 1 minus z inverse, right, with ROC as mod z greater than 1. Now if I multiply this un by a raised to n, then what will happen? Using the property of scaling in the domain, a raised to n un will transform to x of z divided by a, that means it is a inverse z. So z transform will be wherever there is, in this case wherever there is z, I will have to replace it by a inverse z. So inverse z divided by a inverse z minus 1. So you can write it as z divided by z minus a. We have to multiply the numerator and the denominator by a. Now in this case ROC will be a scaled version of the original ROC by a factor of a. In this case the factor is a. Okay. So let us see what is the corresponding ROC for UN. ROC for UN is the area which is outside the unit circle. But now in this case, when we are multiplying by a raised to n, the corresponding radius of the circle will be equal to a, and ROC will be the area which is outside this particular uh, radius equal to a in the z domain. Now consider one more example. Find z transform of fn equal to a raised to n sine n omega t. We already know the transform for sine n omega t. Sine n omega t transforms to z sine omega t divided by z square minus 2 cos omega t z plus 1. What we have to do using this property? We'll have to replace z by a inverse z. So let us put wherever there is z here, I'll put a inverse z sine omega t, a raised to minus 2 z square minus 2 cos omega t, a inverse z plus 1. Now in this case ROC will be mod z greater than a, because for sine term we get e raised to minus a and e raised to plus j omega t. So in that case, magnitude is 1. So the z transform is mod z greater than 1. Now in this case, it will be scaled by the factor of a. Now consider time reversal property. If xn transforms to xz with ROC R, what will be the z transform of x of minus n? That is, if we just reverse the time, what will happen is xz will now become x of 1 by z. So wherever there is z, you will have to replace it by 1 by z, and the ROC, we write it as 1 upon r. So ROC is 1 upon r, means it is the inverted thing, because the z transform is 1 upon z, x of 1 upon z. That is, if z is equal to z1 is in ROC of x1, then z is equal to 1 upon z1 will be in the ROC of x of minus n. Let us consider one example to illustrate this. So consider un. Un has z transform, we know z upon z minus 1 with ROC as mod z greater than 1. Now we have to find the z transform of u of minus n. We'll use the property of time reversal. So we need to replace z by 1 by z. So u of minus n will have the z transform given by, in this equation I'll put, instead of z I'll put z inverse. So z inverse divided by z inverse minus 1. So it is 1 upon 1 minus z. Now note that the term inside this bracket decides the ROC. So ROC will be mod z less than 1. Now for un we have mod z greater than 1. Now in this case, mod z is less than 1 is the ROC. So it is the area inside the unit circle. See, the ROC will be the area inside the unit circle, that is the radius equal to 1. Now consider the property of convolution. If we consider two sequences x1n and x2n with different regions of convergences R1 and R2 respectively, then if we consider x1n convolved with x2n, what will be the z transform? Z transform will be the multiplication of the two transforms. Where will be ROC? ROC will be R1 intersection R2. Always it will be the common area of convergence. So whenever there is convolution in the time domain, there is multiplication in the z domain, and vice versa. If there is a convolution in the transform domain, there will be multiplication in the time domain. So when we write R1 intersection R2, ROC may be larger if the pole zero cancellation occurs, right? So consider the how to interpret this particular convolution property. So consider two sequences, x1z is 1 minus 2z inverse plus z raised to minus 2. That is, the sequence is 1 minus 2 1. There are only 3 points in the sequence. Now x2z is 1 plus z inverse plus z raised to minus 2 plus z raised to minus 3, means x2n, by pulling the coefficients I can write the sequence as 1 1 1 1. Now let us multiply the two transforms. When I multiply the two transform, I am literally multiplying each term by 1 first, then each term by minus 2 z raised to minus 1 first, and then I am multiplying each term here by z raised to minus 2, and I am writing the total expansion. Now if I simplify, I get 1 minus z inverse minus z raised to minus 4 plus z raised to minus 5. So if I want to write the sequence, how the sequence will be 1, then this is minus 1. There is no term for z raised to minus 2 and z raised to minus 3. So I will write 0 0 here. Z raised to minus 4, it is minus 1, and z raised to minus 5, it is 1. So this is the resulting sequence. The reader, the viewer can verify whether this particular sequence is a convolution of these two sequences. So just carry out a convolution and check whether the convolution result is this. Then we have the property of differentiation in Z domain. This is also very interesting property. Now, if xn transforms to xz with ROCR, differentiation in Z domain. So, whatever is xz, we take differentiation of it in Z domain. So, d dz of xz, and it multiplied by minus z, then we get the inverse transform as nxn. So n into xn transforms to minus z dd z of xz. It is the differentiation in z domain. That is why the name of the property is property of differentiation in z domain. We'll illustrate this with one example. So, find the z transform of n square a raised to n un. Use fn as un. So, using the above property two times. See, here I am not considering nxn, I am considering n square xn. So, I will have to use the differentiation two times. So, for un, the fz is 1 upon 1 minus z inverse. Using the property of differentiation two times, we get, if I differentiate this two times, I get this particular transformation. Now, in this case, if ROC is mod z greater than 1, but a pole is introduced at z equal to 0 because there is additional z raised to minus 5 term appearing in the numerator. So, it will give rise to additional z term in the denominator, right? So, in this case, I am considering a is equal to 1. I am not considering a for simplifying the situation. So, we are just considering un, and we are considering n square un, and we are finding out the z transform. If this a raised to n un is considered, everywhere there is z, it will be replaced by a z inverse, right? Or sorry, z inverse will be replaced by a z inverse, and z will be replaced by a inverse z. Okay. Lastly, we will have initial value theorem. If the sequence xn is causal, causal means if it is a right-handed sequence, then x of 0 is limit as z tends to infinity of xz. So, if xn is causal, we know that xn exists for all n greater than or equal to 0. So, there will be a term at n equal to 0, then n equal to 1, 2, 3, etc. up to infinity. That is the meaning of right-handed sequence. So, what will be xz? Xz will be x0 plus x1 z inverse plus x2 z raised to minus 2, just by pulling the coefficients. Now, as z tends to infinity, all these z terms will go to 0, and in that case xz will tend to x of 0. So, this is what is called as initial value theorem. Next, let us try to understand how the time domain behavior will be if we know the pole locations. So, what is the relation between pole location and the time domain behavior? Translate the condition of stability from S domain to Z domain. So, firstly, we know that in S domain, if the poles are on left hand side of the imaginary axis, the system is stable, and if the poles are on the right hand side of the imaginary axis, the system is unstable. Now, in case of Z domain, I can say that the corresponding system will be stable if the poles lie within the unit circle in Z domain, and if the poles are lying outside the unit circle, then the system will be unstable. Okay. Now, this we are considering this Z domain, and in this Z domain we are having real Z and imaginary Z as plotted, and this is a unit circle. Now, the corresponding Z transform has a pole at A. Let us say that it is having the pole at A. Now, in this case, how the system behavior will be? Now, see, this is at n equal to 0, it will be equal to a, suppose I consider, say, a raised to n un. Then a raised to n is equal to 0, it will be equal to 1. Then suppose a I am considering as half. Remember that a must be less than 1, then only it will be stable. So, if I consider a is equal to half, what will be my next value? A raised to n. So, half raised to n. So, it will be equal to 1/4. For n equal to 1, it will be half, n equal to 2, it will be 1/4, n equal to 3, it will be 1 by 8, then 1 by 16, 1 by 32, and so on. Is that right? So, in this case, the system will be stable, and this will be the corresponding time domain plot for ROC mod Z greater than A. The pole is at x is equal to a. ROC is the area outside this circle because it is a right-handed sequence. But because there is a pole at x equal to a, then the corresponding time domain behavior will be shown like this. It will be stable because the pole is inside the unit circle in z domain. Now suppose we consider the pole is outside the unit circle in z domain. Now in this case the system will be unstable, right? So when x is equal to a, suppose I consider the pole is at x is equal to a, which is outside the unit circle. Now in this case how the system response will be? This is for equal to 0, 1, 2, 3, 4, 5. The system becomes divergent. So as n tends to infinity, the system tends to infinity in this case when the pole is at zx equal to a, which is outside the unit circle. That means in this case what will be the value of a? The value of a will be greater than 1. So when a is greater than 1, what will happen? A square, a cube, a raised to 4, a raised to 5. If it is the sequence is a raised to n un. See, this is suppose a is equal to 2, then 2, 4, it will be 8, then 16, 32. So the system will become, system response will become divergent. Now suppose we consider a is less than 1, and in this case I am considering the impulse response of the system given by the sequence not as a raised to n un, but in this case it is n a raised to n un, right. So again I am considering that the pole is at x equal to a, and it is the pole is of order 2 in this case, right. Now how the time domain behavior will be? What I am doing is I am considering the value of a as 1 by 3 and also 1 by 2, and I am calculating the value of xn for n a raised to n. And in this case you will find that this is 0, 0 0.33, then 0 0.22, 0 0.10, 0 0.04. So initially it increases and then decreases. So this again the system will be stable when a is less than 1. Now consider a greater than 1 for n a raised to n un. Now in this case the pole is outside the unit circle at x equal to say 2, and in that case the order of the pole is 2. Now in this case it will diverge because in this case the corresponding values will be increasing because a is greater than 1. Let us say it is 2 raised to n. So 2 square, 2 raised to 3 means 2 cube, it will be 8, then 16 and so on. So it will be a divergent system. So for a less than 1, the system will remain stable, and for a greater than 1, the system will become divergent, whether there is a single pole at x equal to a or whether there is a double pole at x equal to a. Now consider the time domain behavior for a sinusoidal system, a raised to n sine n omega t. We are considering all generalized cases so that you can analyze other cases also. So a raised to n sine n omega t un. So how the system will be? Suppose this a raised to n is not there, it is just sine n omega t. It will just be a sine function, and the corresponding amplitude of this peak will not change. It will be constant, it will be just the sine function. Now when I introduce a raised to n here, what happens is, in this case there are poles at a e raised to j omega t and a e raised to minus j omega t. There are two complex conjugate poles, and these complex conjugate poles being inside the unit circle, what happens is, again the response will be a sine function, but the amplitude of this sine wave goes on decreasing as n increases because a is less than 1. You follow? Now consider the time domain behavior for a greater than 1. As we know, when a is greater than 1, it will diverge. So in this case, there will be poles outside the unit circle. Again, the location will be a e raised to j omega t and a e raised to minus j omega t, but These are complex conjugate poles again, but these will be outside the unit circle. Now in this case, what will happen? The response will be again a sine wave with increasing amplitude. So the corresponding peak for this sine wave will have higher and higher amplitude because the value of A is greater than 1. So the system becomes divergent. Even though the response is sinusoidal, it goes to infinity. It is divergent.